Hello everyone, welcome to the course on Instrumentation and Process Control. Myself Nidhi Mehta, Assistant Professor at Chemical Engineering Department, LJIET Institute of Engineering and Technology. Today, let's just continue with our previous topic which we have started in our previous session of first order system. So here we will start with transient response of step function, that is how step function responds towards our first order system, right. So if a step change of magnitude A is provided in our first order system, so x of t is having magnitude A. So Laplace of x of t can be written as x of s equals to A by s. The transfer function, as we all know, that is a ratio of output by input. So it will be in the form of y of s upon x of s equals to 1 upon tau s plus 1. So same way, putting the value of x of s here, what we can get is y of s equals to A by s equals to 1 upon tau s plus 1, that is y of s upon A by s equals to 1 upon tau s plus 1. Shifting the term in opposite side, we can rewrite this equation as y of s equals to A by s into 1 upon tau s plus 1. Now, we can use partial fraction method. So using partial fraction method, what we can do is C1 by S plus C2 upon S plus 1 by tau, because we are just simply taking tau here in the division form. Next step will be determining the value of constant C1 and C2. This we have already learned in our previous chapters. So using that technique only, we will determine the value of constant C1 and C2. So C1 will be equivalent to A and C2 will be equivalent to minus A. Putting the values in this equation here and then integrating the terms to take inverse of Laplace, we will be getting the equation in the form of y of t equals to A into 1 minus e raised to power minus t by tau, where t is greater than 0, right. Remember this formula, it is quite essential to solve the numericals. Now, let's take one example based on that topic. So, as you can see here, the example is a thermometer having a time constant 0.1 minute. So, tau is given to us as 0.1 minute, is at steady state temperature of 90 degree Fahrenheit. The temperature of steady state, that is x of s, is given to us as 90 degree Fahrenheit at t equals to 0, that is when time is equals to 0. The thermometer is placed in a temperature bath which is maintained at 100 degree Fahrenheit, right. So what we need to determine is determine the time which is needed for thermometer to read 98 degree Fahrenheit. Our objective is to determine what will be the time when the thermometer will show 98 degree Fahrenheit. This is our objective. So as you can see here, tau is 0.1 minute, which is time constant. So tau is 0.1 minute. X of s is our steady state temperature of bath, which is given as 90 degree Fahrenheit. A is the magnitude, that is difference between steady state and the ultimate temperature, that is the highest temperature. So 90 is the reading of thermometer and 100 is temperature of bath. So difference between them is the magnitude A. So 100 minus 90 is A, which is 10. Now The ultimate value can be determined as yt equals to a 1 minus e raised to power t by tau. What is yt? Our ultimate value here, what we need to know is 98 degree Fahrenheit. We need to determine when my thermometer will show 98 degree Fahrenheit. So we need to determine y of t. Y of t is basically present value minus steady state value. So present value I need in thermometer is 98, steady state value is 90. So 98 minus 90, that is 8. Yt is 8 written here, equals to a, which we have calculated as 10, 1 minus e raised to minus t by tau. Now simplify this equation. So just take log of this equation and you will get the value of t as 0.161 minute, right. So this is numerical which is based on step input for first order system. Now let's discuss a new topic which is liquid level system. Liquid level system is basically a first order system where we need to determine a relationship between input of the system and output of the system. So here we are considering this tank. As you can see here, we are having a tank system. A tank is a liquid level tank, right. Input flow rate Qt is inlet volumetric flow rate, Q0T is outlet volumetric flow rate from the tank. The height of liquid inside the tank is h of t, right, and R is the resistance which is offered to the outlet flow rate. So now here we are considering that cross sectional area of tank is capital A. R is the resistance here, as you can see, which we are offering. Density of this fluid or liquid we are assuming as rho, right. So what we need to initially determine is this Q0. So let us assume that Q0, that is the volumetric flow rate through the resistance, is given by h by R. Why? Because the volumetric flow rate at the outlet will depend on the head or height of liquid inside the tank and resistance. More the height of liquid inside the tank, more will be the flow rate or volumetric flow rate Q0, and more the resistance offered, less will be the volumetric flow rate from the outlet, that is Q0. So more the height, more will be the volumetric flow rate, more the resistance, less will be the volumetric flow rate. So we will develop a relationship between Q0, R and H. So it can be written as Q0 equals to H by R. Now our next step is to apply a material balance around this tank. So mass flow in, that is Qt, mass flow out, this one, and equals to rate of accumulation of mass inside the tank. So what we can do is, we are talking about mass, here it is volume. So we will multiply volume with density to get the mass. So that's why we have done as rho into Q, that is inlet flow rate of mass, rho into Q0, outlet flow rate of our mass, rate of accumulation, how much volume of liquid is inside the tank, can be determined as height of liquid inside the tank or head of liquid inside the tank multiplied with cross sectional area of the tank, right. So area into height will give us volume, and that volume when multiplied with density will provide us mass. So d by dt of rho A into H. This is a material balance equation for our given liquid level system. Now next step will be combining of both the equation. What we will be doing is, instead of writing Q0, I will use equation number 1, h by r. So this is q into rho minus rho h by r equals to d rho h by dt. Taking rho common from this particular equation, we can get as q minus h by r equals to rho dah by dt, right. Now what we can do is we will simply use initial condition. So initially, that is, we will consider that steady state condition. At steady state condition, we know that there is no change in any kind of parameters or variables. That's why d by dt term will be changed to 0. So it can be written as qs minus hs by r equals to 0, where s indicates the steady state condition. Now simply take both the equations, subtract this equation number 5 from equation number 4, right. Subtracting equation 5 from equation 4, what we can get is q minus q of s minus h by r minus hs by r equals to a d h minus hs by dt, because this term is ultimately 0, dhs by dt is 0. So it is the same thing. Introducing deviation variable, instead of writing q minus q of s, we can simply write capital Q. Instead of writing h minus h of s, we can write capital S, right. So q equals to 1 by r h plus a dh by dt. Now take Laplace of the given equation and shift the term. You will be getting h of s upon q of s equals to r 1 plus a r s. Here a into r can be taken as tau, which is our time constant. So for the given liquid level system, the value of tau or time constant is a into r. This is the desired term for our given equation, right. Hope all the things which we have covered today is quite clear. Thank you.